Hello everyone, welcome to the video chapter 11.5. In this chapter, we are going to talk about chemical properties of amines. For this chemical properties of amines, the reactions, it refers to the chemicals test. Okay, so first of all, we are going to look at this HINSBERG's test. So the functions of this HINSBERG's test is used to distinguish between primary, secondary, and tertiary amines. Both aliphatic and aromatic have the same reaction. That means primary ali and primary aro, they have the same reaction. Okay, similar to this secondary and tertiary amines. So it doesn't differentiate which one is aliphatic, which one is aromatic. So it depends only on the class of amines. So for this HINSBERG's test, it involves two steps. First steps, mixture containing small amount of the amine and benzene sulfonyl chloride is shaken with excess potassium hydroxide. And the second step, after allowing some time for the reactions to take place, the mixture is then acidified, which means react with HCl. So if you look at this primary amine, for example, using methylamine, so there is a CH3 group attached to the nitrogen's primary amine. So when you react with this benzene sulfonyl chloride, so identify that how are you going to take out the side product HCl. Okay, so where you break the bond is where you form the bond. So the nitrogens connect to the sulfur in the first step. So when you have the reactions with the excess potassium hydroxide, these hydrogens, the extra hydrogens in your primary amine is going to react with the base. So hydrogen substitute by the potassium cation. So you have this K plus and minus, which is an ionic salt. Okay, so an ionic salt is soluble in water, so you're going to see a clear solution in this first step. And then after that, when you react with the HCl in your second step here, the potassium ion will then replace with the hydrogens. Okay, so K plus replace with these hydrogens. So when you have these structures, it will become water insoluble, in which you are going to see white precipitate. Okay, so primary amine, clear water at clear solutions at the first step, white precipitate at the second step. Alright, so for secondary amines, also the similar thing. So using a dimethylamine as an example, so you can see there's still an extra hydrogens over here. So when it reacts with this benzyl sulfonyl, you're taking out the hydrogens and the Cl. So there is a side product HCl. So you're forming a bond between the nitrogens and the sulfur in the first step. Okay, so this is a white precipitate, like as you doesn't see any cation and anion. So this will be a white precipitate, okay, which is water insoluble, first step. Second step, there will be no reaction because there's no K plus for you to replace. Okay, second step over here, no reaction. So the precipitate from your first step will remains unchanged. So for the secondary amine, white precipitate and white precipitate for both steps. Whereas for this tertiary amine, if you look at this example, we have trimethylamine. When you react with benzyl sulfonyl chloride, there will be no reactions because in this tertiary amine, it doesn't have hydrogens atom. So no reaction in the first step. So no reactions, you're going to see a clear solution. But for the second step, this amine, the original amine, will react with the acid. So base react with acid. So you're creating this ionic salt. Okay, ammonium chloride salt, which is water soluble. Ionic salt is soluble in water, so you're going to see clear solution. So tertiary amine, both steps you're going to observe clear solution. So for the summary of this HINSBERG test, you can see that primary amine, in the first step, you're forming clear solution, white precipitate in the second step. Secondary amine, white precipitate and white precipitate. Tertiary amine, clear and clear solution. So it differentiates between different class of amines. So take note that there is a typing error at the tables over here, benzene sulfonyl. Next chemical test or the next chemical property we have for amine is this nitrous acid test. So this nitrous acid test is to distinguish between aliphatic and aromatic, primary, secondary, tertiary amines. So both aliphatic and aromatic, they have different reactions and observation. So nitric acid has a formula HNO2, which is a very weak acid and very unstable. So usually we are going to prepare in situ. So in situ means that you prepare on the spot. Okay, on the spot, that means we are going to use these combinations of reagents and condition. So NaNO2 together with an acid, HCl or sulfuric acid, and then the temperature 0 to 5 degrees Celsius. So prepare in situ. The examples given over here, as long as you can get this nitric acid. Okay, either you use HCl or H2SO4. Alright, so let's look at this primary aliphatic amine. So you can see this is a general formula for your primary aliphatic amine where we react with this nitric acid in situ. We are first forming this aliphatic diazonium salt, which is highly unstable. Because it is very unstable, it will then break down to release the nitrogen gas. And then imagine that after you release the nitrogen gas, you are forming this carbocation. So this carbocation will then form an alkene, alcohol, alkyl halide. So for this primary aliphatic amine, you are going to form 4 products altogether. Okay, alkene, alcohol, alkyl halide, and also nitrogen gas. So looking at the example given down below here, you have 1 propanamine. Okay, a primary aliphatic amine. So when you react with this nitric acid reagent, you are going to form propene. So remember to take notes at the number of carbon. So imagine here is your amino group. So after you break up, so you're going to release this nitrogen gas. And then right after that, you need to imagine that I will generate a primary carbocation over here. And then I'm going to form a double bond in between these 2 carbons to form propene. And then imagine over here, I have my positive carbocation. Because this is a primary carbocation, I'm going to do rearrangement so that I produce a more stable secondary carbocation, which then will react with the H2O to generate this propanol. Okay, so take note on the positions of your OH group at the second carbon here after rearrangement. So similarly for this haloalkane. Okay, so after rearrangement, the Cl will attack at the more stable secondary carbocation to form this haloalkane. But anyway, for this primary aliphatic amine, we are going to generate 1, 2, 3, 4 products altogether. And the observations for this chemical test, you are going to see gas bubble evolve at any temperature. So because this diazonium salt is very unstable, so at any temperature, we are going to observe gas bubble, which represent this nitrogen gas. And then for primary aromatic amine, for example, we have this aniline. So when it undergoes this nitric acid test, we are going to form a diazonium salt, which is slightly more stable if you keep the temperature below 5 degrees Celsius. So it will remain at this diazonium salt. So a diazonium salt is far more stable than the alkyl diazonium salt. It is a very useful intermediate in various syntheses. So we're going to use this diazonium salt later. Okay, so for example, over here, you can see this nitrogen is directly attached to the benzene. Okay, therefore, this is a primary aromatic amine. So when it undergoes nitric acid test, you're going to get this diazonium salt. So observations different from the aliphatic amine, no gas bubble evolve below 5 degrees Celsius. You must label the temperature because if it's beyond 5 degrees Celsius, you are going to see gas bubble. Okay, in another meaning, if it heated the solution, still it's going to break down to form nitrogen gas. And then let's look at this secondary aliphatic and aromatic amine. I classify both together because it will show you the same observation. So both alkyl and anhydride secondary amines react with these nitric acids to yield N-nitrosol amines.
Okay, so this is the general formula in which when you have this secondary amines, the hydrogens, the only hydrogens that attach to the nitrogens will substitute with this N double bond O, which we call it as the nitrosol substituent. Okay, N-nitrosol because this NO group attached to the nitrogen. Okay, so hydrogens substitute with the N double bond O, N-nitrosol amine. So for example, if you have this dimethylamine, okay, so the hydrogens replaced with this N double bond O, and the observations, you're going to see a layer of yellow oil form. So this is aliphatic secondary amine. And if you have the aromatics one, it's still the same. You're going to form this N-nitrosol aniline. Okay, still the same. The hydrogens is going to replace with this N double bond O, which you are going to observe yellow oil form. Next, we have this tertiary aliphatic amine. Alright, generally this is your tertiary amines, and then you're going to see this amine salt in which we produce the N plus, okay, and also N-nitrosol ammonium. So when a nitrogen is having 4 bonding, you're going to see a positive charge on this nitrogen. Okay, so for example, trimethylamine, you're going to form this trimethyl ammonium salt and H plus with another 3 alkyl group, and then this N-nitrosol ion. So observation, clear solutions form because we are forming the ionic salt. So you're going to see clear solutions only. Whereas for this tertiary aromatic amine, it will undergo electrophilic aromatic substitutions with this nitrous acid. And the product form is para isomer. That means it substitutes at the para positions number 4. And this is due to the bulky dialkyl amino group block the approach of nitrosonium ion to the auto position. Okay, so for example, so if you look at this N-dimethyl aniline, so here you got 2 methyl group. So when it reacts with this nitric acid, it cannot substitute at the positions auto or meta, but it's only substitute at the positions para. Okay, so for this nitrosol, it will attach at this carbon number 4. Okay, so 4-nitrosol because it's attached at carbon number 4 in the benzene. So the observations of this nitrosol aniline for tertiary aromatic amine, you're going to observe green precipitates. Okay, for this chemical test, tertiary aromatic amine, green precipitates form. So summary for this nitrous acid test, if you look at this primary aliphatic amine and aromatic amine, there's gas bubble release at any temperature. And then for these observations, no gas bubble release below 5 degrees Celsius. Secondary ali and aromatic amines, going to see yellow oil form. Tertiary aliphatic, aromatic, they both have different observations. One is clear solutions, another one is green precipitate. So this one taken out from the notes, so have a look at this. So chapter 11, beside HINSBERG test and nitric acid test, we still got one more identification test for aniline. Okay, only for this aromatic primary amine, which is with bromine water. So amino, the NH2 is very powerful activating group and a powerful autopara director. Autopara director, that means they will direct the substituents towards the auto positions and the para positions, positions 2 and positions 4. So aniline will react with this bromine water, no catalyst is required, and the incoming Br atoms will substitute the hydrogens at the auto and para positions. So this is your aniline, bromine water, and then it will substitute at the auto position, which is positions number 2 and positions number 6. Okay, positions 2 and position 6. Para positions is positions number 4. So the products over here, you're going to observe 2,4,6 tribromo aniline, which is also one of the identifications tests for phenol in chapter 8.5. Okay, so bromine water can react with phenol as well as aniline. The observation is the same. Last year, you're going to observe white precipitates form. All right, and come to the last reactions of this amines. It's known as coupling reaction. So coupling reaction is the name of the reactions as well as the type of reaction. Okay, coupling reactions. That means you're making a couple of this diazonium salt. So aride diazonium salt react with phenol and tertiary aride amines to yield azo compound. Okay, the reagents is either you're using phenol or tertiary aride amine. So tertiary aromatic amine. Okay, so this one is in general. So you have this aride diazonium salt, quite stable, below 5 degrees Celsius. And then for this one is your reagents condition is either a phenol or a tertiary aride amine. Okay, tertiary aromatic amine. So you're going to form this azo compound, which is also known as a di. Okay, so indicate that where are you forming the bonding. So from the triple bond end and triple bond end, it opened up into double bond and then making another new bonding with this reagent. Okay, and then take notes that you are forming the bonding at the para positions of the phenol and the tertiary aromatic amine. Okay, so this is the para positions. So many dyes and pigments belong to the class of organic azo compounds. So these azo compounds are usually very intensely colored and relatively inexpensive compound. A common azo compound we know is the paints. So here's the examples of these coupling reactions. So the structures of your diazo compound when you react with phenol. So you're making a bonding at these positions. Okay, so the reactions over here, madam, just roughly show you the mechanism so that you can understand that how are you going to form the bonding at these para positions. So taking the double bond, it imagines that this phenol, we have the benzene, which have alternate double bond. So we are going to attack the nitrogens and then push away the triple bond to form double bond. Okay, so you're making a bonds over here at the para positions. Similarly, if you have a tertiary aromatic amine, still we are going to use a para positions over here. Attack at these nitrogens, pushing away the extra bonding towards the positively charged nitrogen. So forming the bonds over here. If let's say you got the structures p dihydroxybenzene, so for this one, we cannot substitute at the para position. Okay, so we have to take another carbon to form the new bonding. So let's say in this example, clearly you show the alternate double bond. So taking one of the double bond, attacking at the nitrogens, and then open up the triple bond. So you're forming the bondings at either of these carbons. Still, you are going to get this final product. Okay, so this is the examples of your azo compound, okay, which is very intensely colored. Alright, so that's the end of our chapter 11, and please have a try at the exercises given. So thank you, and I'll see you again.